Once upon a time, you learned that the electromagnetic wave has two components. One is an electric field that goes up and down, and the other one is a magnetic field that goes left and right, and they oscillate together in this nice little dance. So it looks something like this, where one is electric field, oscillating electric field. Wow, how do we understand this? I don't know. It's not in our syllabus, so I just need to know that it oscillates. But you also have a magnetic field that is oscillating sideways. And if you put both planes together, you have the magnetic field, flat, and the electric field, vertical, and you get 1, 2. This is your electromagnetic wave. And people said, oh, this is our visible light. And it was pretty well established that light is a wave. But then, everything changed when one fine day in Germany, somebody observed something. So this dude, Heinrich Rudolf Hertz, you have heard his name Hertz before. It's a unit, by the way. When he was doing something related to radio waves, which is electromagnetic waves, he saw something is off. He's like, I observe a weird phenomenon. Hertz said, when I shine a UV light, like this lamp, on a piece of metal, let's say for example zinc, he discovered that when the light is a certain frequency, suddenly there's something happening in his circuit. Of course, he didn't see all these things flying around, but he says like, there are sparks in my circuit. There's some kind of current that I'm measuring. I'm not sure what is going on. Why do I measure some kind of electricity when I shine light on a surface? Now that's weird. So he probably made some little note and told people like, oh, something's up. And not too long later, another German physicist, Philipp Lenard, in 1902, also said that he observed something similar. Like, why is it like electricity when you shine light on a metal plate? And he suspects that, maybe it is these things called electrons that were just discovered in the 1900s or so. Maybe these are the things that come out once you shine light on them. But why? They had no idea. They're just like, something is strange. It's not making really much sense until another guy came along. Now this guy, also in also a German physicist at the time, Albert Einstein. Look at that meme face. He's just like, you guys, this is new physics that we have not discovered. He said, do you guys know? Actually, maybe light might not just be a wave after all. You guys keep saying light's a wave, but that doesn't really quite fit with your observation. So he started coming up with an equation. He says like, well, actually light could be a wave, but maybe also a particle. Both? And he came up with this equation to measure the energy of a wave and thought about a new way of thinking about light. But before I go to the end of the story, let's go and take a look at this photoelectric effect a little bit more. The one that Hertz started looking at. So what is the photoelectric effect? For this, you need to remember some things for A levels. The definition. What is the photoelectric effect? And right here is what you need to remember, the definition down here. Photoelectric effect is what was observed, so it is the release of electrons. From where? From the surface of a metal. What happened when you shine light? Don't say shine light. We're going to use the scientific term, which is when there is an electromagnetic radiation is incident on its surface. Incident means shining on the surface. So something like this picture up here, okay? You have some electromagnetic radiation shine in, and who comes out? Electron comes out. But then again, there was some confusion because they say, wait. We used to think that light is a wave, but there are some problems with that model when we try to explain the photoelectric effect. So here are the two explanations. There was some argument. The people were like, what? Einstein, your explanation does not make sense. Why would a light be a particle? And these guys are like, I don't know. The observations are just like that. So let's go through the possible explanations and we see which one makes more sense at the end. First one, classical wave theory. This camp of people were saying that electromagnetic radiation is a wave. Of course, it's a wave. We learned about this for so long. The speed of light equals to F times lambda, which was what you guys learned in AS. The speed of electromagnetic wave is this. C is speed of light, 3 times 10 to the power of 8 meters per second. And yeah, it's an oscillating electric field and magnetic field, and that's your electromagnetic wave. It's a wave, guys. But then here comes Einstein and all the other crazy people who says that actually, guys, electromagnetic radiation is a particle known as photons. There's a name for it. And what is a photon? Okay, let's define a photon. Look at these cute things. These are not biology cells. These are called photons. I mean, we just draw it that way. So what's a photon? There's a definition for it. Photon, we call it a discrete packet, or you kind of say a quantum of energy. Quantized energy. Quantum of energy of electromagnetic radiation. Yeah, something like that. So one camp is like, oh hey, it's a continuous stream of energy wave. Others is like, nope, it's burst of packets, like bullets, you know, we go bullets of light coming through, hitting the surface and releasing electrons. Okay, so they're like, we can't settle our differences. Okay, let's continue on to the other observations. So camp 1 was saying, energy of radiation is continuous because a wave, you know, the wave just keeps going forever and forever. And that is, where is that? Let's draw it here. Continuous, just keeps going forever. And this one, the energy is related to its intensity. Related to intensity. And we learned before that the intensity of a wave is related to its amplitude squared. So whatever amplitude this is, that's what energy it has. And this energy is continuous stream of energy coming into the metal. So I'm going to write here, continuous. Okay. But then, if you want to think of the photon model, it's discrete packet of energy. Each of these photons have a certain energy depending on their wavelength. That's what Einstein was arguing about. So the idea is that energy is discrete versus continuous. What does discrete mean? Can be calculated using Planck's equation. So Einstein and Planck, they kind of use each other's stuff. So the energy of the photon, each packet, like you know the parcel delivery sends you something you ordered online, each packet can be calculated with E equals to HF. Now this is an important equation you will use a lot in here. Okay, and by the way, Planck's constant is new. We have not seen this before, but you can go to the every past year question. The first page will tell you what Planck's constant is. The H, Planck's constant, has a certain value that Max Planck discovered. So that is 6.63 times 10 negative 34 joule second. It's in base SI units. So there we go. Planck's constant. Okay. And this thing is the idea of photons as energy. So in 1905, Einstein was trying to tell people that, look, you have a wavelength, your wave, right? You can treat them like photons, but you can calculate the energy with that equation that we just wrote just now. For example, if you have a wavelength of 400, E times HF is 3.1 EV. Oh, yo, what is EV? It's another way of expressing very small amounts of energy. So joules and EV, you can convert between them. So when you have a very short wavelength, very large energy, 3.1. What if you go over to a longer wavelength, 600? Lesser energy. You gotta remember the relationship between wavelength and energy. If you go to very long wavelength, see 681. Wow, very low energy, that 1.8. So the smaller the wavelength, the higher the energy it is. And this is only in the visible light spectrum where you can see with your eyes. So how did Einstein come to this idea of, hey, actually maybe it's photons? Here's the observations, 1 and 2, that we're going to look at, starting from here, observation. So observation number 1, when you shine light onto the surface, if it's a wave, photoelectrons will only be emitted after a time interval or delay. Time interval or some delay. Why? Because as the electron in the metal receive enough energy, then only after they receive enough, then only they start to escape. And that makes sense to a lot of people because they're like, yeah, the wave come in. The electron down here will take some time to reach the top, then only they escape. But then, what was actually observed after people did a lot of experiment, they say, actually it's instantaneous. The moment you shine light, electrons start to come out. Oh. So that's a conflict. They say like, it's supposed to have a time delay. But when you observe it, it's actually instantaneous. Why? And there's a second problem. If you have a certain frequency, no electrons will come out at all. So no electrons are emitted if the incident photons have a frequency below a minimum frequency. This is what we call a threshold frequency. Threshold. And no matter how large the intensity is of this incoming electromagnetic radiation. You see, at certain frequency, if I put at 400 nm, which is what frequency? I don't know, some frequency lah, nothing comes out. You can change the intensity to very high, very low, nothing comes out. But if you crank up the frequency a little higher, then suddenly you will start to find that electrons start to come out suddenly. Huh? Why must pass a minimum frequency only electron will come out leh? That's the part where there was a conflict. Another point of conflict was between these two is that in the classical wave theory down here, number 2, supposedly as the intensity of the radiation increase, then the electron will receive more power. So then they will have a larger maximum kinetic energy. So maximum kinetic energy of the photoelectrons will increase because intensity means energy. So if intensity is more, then the kinetic energy of the electron, when they come out of the metal, should be also higher. So what is intensity again? Intensity is related to your amplitude for waves, or amplitude square. So this one is small intensity. Then if you put large amplitude wave, I try to draw large amplitude, then the Ke, the kinetic energy of the electron as they come out, should be much faster. But it wasn't observed that way. They were like, actually no, intensity is something else. So if you look on the right side, how do you define intensity for all these particles? So people define intensity as not the amplitude square, but intensity here they define as the number of photons. Higher intensity, more photons, more bullets coming in to hit the metal. So that was the last part down here, the final blow. As intensity of the incident photon increase, what that means is more photons, the number of photons are hitting the metal surface. Hence, a greater rate of emission. That's just why it changes. Intensity doesn't change maximum Ke. This one is nope. Intensity just change, more electrons come out. That's all. So what actually intensity does is that when you increase the intensity of all this light coming in, the radiation coming in means more photons. That just means it doesn't affect. You just have more electrons released, but not exactly the energy of the photons affected. Only by increasing the frequency of the incident photons, then you can increase the maximum Ke. So quantum theory, all these on the right side, all these ideas kind of threw a bomb into the classical wave theory group, and then they're just like, have all we've been studying and teaching in universities been a lie all this time? Well, later we'll find out that both camps are kind of correct. But in the photoelectric effect, it makes more sense to explain, based on the observations, it makes more sense to use quantum theory to explain why the photoelectric effect happens the way it does with all the measurements that we have looked at. Okay, so make sure you know the separation of both of these ideas. If you want to argue with classical wave theory, what are your points? If you want to argue with or explain the effect with quantum theory, what are your points? And it turns out quantum theory wins for this round in the photoelectric effect. So after much playing around with experiments, and they realized like, oh, actually, light is a photon, not wave. I mean, for this effect, maybe you want to think about it in photons. Yes, they are waves, but they are also photons. And you can think of it as each photon come in, release an electron. Each photon come in, release an electron. So it's instantaneous release. And when you crank up the intensity, what it means? More photons. So more photon. More photon come in. Less photon, then you crank down. So you see, only like 1 come out, 2 come out, less photons coming out. So less electrons release. Well, how about energy? How fast they come out? Well, that depends on what frequency these photons are. So let's crank it down and see what's the minimum we can go. Still got electron coming out? Oh, no more liao. Oh, so we have passed the minimum threshold. Okay, let's go up a little bit. Higher frequency. Oh, coming out already. But these are very slow, not very low energy. So their maximum kinetic energy is much lower. But if you crank it up to very high energy, high frequency, then you see they come out so fast. Very high kinetic energy when they come out. Okay, so this is all of them coming out. So that's how you can think of both of these models. So 10 years after Einstein came up with this idea of E equals to HF, Robert Millikan, an American physicist, came along and did some experiments like the one you saw just now. And he's like, by golly, I think you're right, Einstein. And he verified Einstein's equation along with the others. And finally, the world's like, okay. We thought Einstein was crazy. I guess he's not. And so Einstein won the Nobel Prize. Woohoo! Nobel Prize in I forgot what year, but it was for the photoelectric effect. I think 1921. If you're very adventurous, you can go search up that paper and see how he actually thought. But this genius was way ahead of his time, and he was like, you guys, this is new physics. Y'all don't know, but it's new physics. So in the coming video, you will learn more about this experiment, photoelectric experiment. What did Millikan do? What's the tube? There's another name, another guy who did more experiment, but you'll learn about the setup, how they studied the photoelectric effect. And we will also look at Einstein's full equation. This is not the full one yet. There's another full equation for the photoelectric effect. But just remember for today that today the winner is quantum theory model. So wave model doesn't really explain the photoelectric effect. But it doesn't mean that light is not a wave. Light is still a wave. But also, we have a new way of understanding light in terms of photons. So incoming incident photon hit a certain metal plate with a certain what we call work function. We'll learn more about this in the coming video. Each type of metal have their own work function. And once these photons hit the plate, pew, 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 like bullets hitting a metal sheet, electron will fly out. So it is called emitted or ejected electrons, and all these will have different kinetic energies. So a range of kinetic energy. So some, let's see if I can change this arrow a bit. This one is K1, KE1. Maybe you have one that is even faster, KE2. Maybe you have another one that is super fast when it comes out, KE3. Why do they have different energies, and how do we calculate the maximum KE? So this is KE max. That will be in the coming videos where we'll learn more about photoelectric effect, the equations, and the experiment setup. That's all for this intro video. I will see you in the next section.